So, welcome. This will be the first lecture on internal forced convection. So far we have done external convection. So, the external convection does not have any imposed length scale associated with the thing. Now, in internal convection we will see that there are certain things which makes it a little bit different from internal convection, internal forced convection. So, the first thing that we are going to look at is basically laminar duct flow, duct or pipe flow. Okay. It can be a channel, I mean like two parallel plates. So, if there is a flow going through it, okay. It can also be a pipe with a flow going through it. It can be varieties of other things. Okay. It can be like this kind of a pipe also. That will be a little bit difficult, that analysis, to do this kind of sections. Okay. There can be a flow through sections like this, there can be flow through rectangular sections, there can be flow through triangular sections, any type of sections. Okay. So, these are all comes under the umbrella of internal forced convection. Okay. So, of course, these things are a little bit difficult to analyze, okay, not impossible, difficult to analyze. So, we will start with a very simple one, again a canonical problem, to show you how things can be generated. Okay. And then we will take it forward to the next level. Okay. So, in this particular case, okay, if we have like two parallel plates, okay, and then there is a flow, once again this is a uniform flow u which is approaching the plate, right. This distance between the two plates is basically given by d, which is basically equivalent to the diameter. Okay. So, it can be a pipe also, but the plate is easier because we deal with Cartesian coordinate system, but the same thing can be done for a pipe as well. Okay. So, there is no hard and fast rule about that. Now, so if you look at this particular problem now, the interesting feature is that this is now a bounded flow because there is a boundary on both sides, right. So, there is no extension to infinity. Also, the moment this flow sees this plates, okay, the boundary layer that we developed earlier will start to develop here as well, right. So, the boundary layer is natural, it is going to happen. That means the boundary layer will be the region where the viscous drags will be important. That means the flow velocity will show a curvature, and so that is going to happen. But now, it will happen symmetrically perhaps from both sides of the plate. That means from this side of the plate also it will develop, this side of the plate also it will develop, right, because there is, we suppose that there is no preferential bias, right. So, as it develops, what happens is that these two boundary layers then merge with each other. So, this is the boundary layer delta, this boundary layer now merges with each other, right. The two boundary layers will merge, because again this is not an infinite reservoir. So, the boundary layer cannot go on extending up to infinity. So, it will merge and basically converge with each other. Okay. So, beyond that, okay, beyond this particular length, okay, you can see that everywhere in the flow the viscous drag is important, right, because the boundary layers have basically covered the entire pipe, duct, whatever you call it, right. So, in this particular section, let us mark this important piece of section. Let us call it something like a xh. Okay. This is of course 0. Okay. So, when x is less than xh, okay, we call this flow to be developing, right. When x is greater than xh, we call the flow is fully developed. Okay. So, we call the flow to be developing, and we say that the flow is fully developed depending on what is the value of xh. Okay. So, before xh let us see what happens, after xh let us see what happens. Okay. So, the interesting part will be when you look at this particular section, the section, this particular section actually, the developing region of the flow, what do you see, that what will happen at the center? That means in this particular region, this is called the core, okay, or in other words it is called the potential core. Okay. So, the name is a potential core. Why is it called the potential core? Because the viscous effects are not important. So, you can apply your potential flow solution which you learned in your fluid mechanics here. You can apply your potential flow solution here, there is no problem, right. Except here, of course, the potential core does not mean that the flow velocity does not change in the potential core. Flow velocity changes in the potential core, but it does not change due to viscosity. Okay. So, that is what you are getting in your potential core region. Okay. So, in the potential core region there will be a velocity profile which is different from what the velocity profiles are in the boundary layer. After it has merged, that means beyond x by h, right, we can apply the full fledged Navier-Stokes equation to solve it there, right. So, in the developing region there are two parts. Inside the boundary layer it is basically the boundary layer equation or the Navier-Stokes equation. In the core region you apply what we call the potential core solution. Okay. Beyond x equal to xh, okay, the entire thing is basically Navier-Stokes or the boundary layer solution, whatever we will find it prudent over here to apply, right. So, how would the velocity profile actually look? So, let us look at this. Once again we can prove that this will be the velocity profile. So, let us once again draw this profile. This is smooth. Okay. So, in this particular area, as many of you would know by now, the velocity profile is something like this, right. Forget it, this is not at an angle, this is actually all along the axis of the duct. Okay. So, this is a parabolic profile, we will see how it becomes parabolic. Okay. And this profile actually we will find does not change with distance. Okay. So, you can take this profile and put it here, it would be the same. Okay. So, there is no change in the velocity, that is a fully developed profiles feature, that the velocity profile should not change. What about here in this particular section, right. In this particular section what will happen if I draw it properly, okay, you will have that there is a rise from both sides like this, right, and then there will be some kind of a potential core like that, right. So, up to this it is basically the boundary layer, then after that it is the potential core. Okay. This potential core, that means the flat region, right, okay, that will accelerate as you go to the next level. That means this is the profile at x1, if you take another at x2, okay, you will see that this potential core velocity or the velocity at the potential core, there is only one single velocity because the flow is uniform there, it will increase with distance. Okay. And you can readily make out why, that is because as the boundary layers are extending, okay, the flow velocities are changing, right. So, in order to maintain a constant mass flow rate through this conduit, you have to have an increase in the central line velocity, right. Okay. But after the x equal to xh, the velocity profiles will be self similar in nature. Okay. So, some of these things we will prove, so do not worry, but this is kind of intuition that there is an entrance length where the boundary layers are developing, and then there is a fully developed length where the boundary layers do not vary. Okay. So, depending on, so it is not just with hydrodynamic boundary layer, this is hydrodynamic obviously, there will be a thermal boundary layer also which will come in due course, okay, over here. Okay. So, let us do our standard analysis, okay, and see that if we can extract some scales out of this particular problem. So, at the fully developed region, okay, you know that your delta will scale as d by 2, right, it has to scale as d by 2, right. Okay. Now, in the entrance length, that means in the length where the profile is still developing, okay, if we can apply the equation how does this come? It is the same way as your external boundary layer. This particular terms comes from the pressure. The pressure in the potential code is basically imposed into the boundary layer, right, and this comes from the Euler's equation therefore. Okay. So, the pressure term is substituted by u c duc by dx, okay, and that comes from the potential code solution. Okay. So, now we can do our standard scaling analysis on this. So, the first two terms in this series ux square by x, okay, okay. So, is actually proportional to, okay, got it. Okay. So, this will be u c square by x, and the second term, this particular term will be that, right. So, this gives you delta scales as gamma x by u c, or gamma by x gives you gamma u c by x. Okay. That is what you get out of this. Okay. Now, you already know from your Blasius solution that delta by x is equal to 4.92 into Reynolds number to the power of minus half. Am I right? So, that is what you know that is going to happen. You substitute that over here. Okay. You substitute the expression for that over here, okay, because this is a scaling argument, that is an exact equation that you got from your Blasius solution, right. So, this is of course not strictly applicable, but we are going to take a leap of faith and use it over here. So, this is Blasius solution for flat plate, got it. Okay. Now, in addition to that, we apply one more equation, that delta is equal to d by 2 at the point where the entrance length ends. Okay. So, combining these two equations, therefore, you will get x by d will be equal to 0.01 Reynolds number to the Reynolds number d, okay, where Reynolds number with respect to d is actually gamma d by u c. This is not the same as Reynolds number to the power based on x. So, the length scale is just d, okay, instead of that. So, this gives you that your x, that is at the point where the two boundary layers actually join, okay, is given as a function like this. Okay. It is given as a form as I have mentioned in this particular equation. Okay. This is roughly what we call 1/10, right, okay, of the Reynolds number, right. Okay. So, x by d ratio at the point where you actually have the two boundary layers merge, okay, is given by 0.01 of Reynolds number based on d. Okay. Now, from the integral formulation we can try to extract the same thing, because this was done rather heuristically, okay, because we just took the scaling from the Blasius solution and kind of applied it here, which is strictly not the correct thing to do, but we kind of got away because these can be constituted as two parallel plates. Okay. One plate is at the top, one plate is at the bottom. So, you can consider it like to be two parallel plates kind of independent with respect to each other. Okay. Now, in the from the integral solution, integral formulation, okay, we can apply it directly. Look at this form u c to u into dy plus duc dx. Okay. That is the integral formulation, okay, that we had earlier. From mass conservation, what we can write? Try to understand this particular expression at any point in the entrance length. Okay. The total mass is given by this. This is what the mass that is entering inside the duct, right. So, that is rho ud by u, and u is constant. So, this is the total mass that you are flushing in. Now, inside the boundary layer it will be rho u into dy, just outside the boundary layer it is rho uc into dy, right. So, these two terms when they are added you should give you the final expression. So, this is the conservation of mass, right, there is no ambiguity in this. This is the conservation of momentum, right, the previous equation, okay, where you can also see this is of course u, don't, okay. So, where we have just done the momentum expression in a very similar way that we saw earlier, okay. So, these two things are already kind of known, and it's very intuitive. So, you can assume now, like last time, I am not going through the whole steps because you can work it out yourself. You can assume a polynomial profile and then you can evolve through the boundary conditions, because that is not the intention. The intention is to just give you guys an idea that how this is to be done. So, you can assume very similar to the velocity boundary layer over a flat plate, you can constitute a similar polynomial profile for u by uc in the entrance length, that means in the developing part of the whole thing, okay. So, that you can easily do, okay. So, now applying this particular form into the continuity equation that we have here, okay, what you will get is okay. That is what we have done over here, and now if you just substitute now this into this particular form, you will get this is y squared by delta y cube by 3 delta square 0 to delta plus d by 2 minus delta okay. Now, it is easy to integrate 2 delta by 3 plus d by 2 minus delta u by uc d by 2, or in other words u by uc 2 by d d by 2 minus delta by 3, then u by uc or uc is equal to u to 3d divided by 3d minus 2 delta, okay. Or in other words, from here you get 2 delta by 3d into 1 minus u by uc, or delta by d by 2 3 into 1 minus u by uc, okay. So, here of course, as you know, uc is a function of x only. That is the reason we could do such a lot of things, right. It is a function of x only. This has got no dependence on y, because at any particular y section you saw that uc was constant, right. If you do not recall, this is the way. So, if you recall the profile at any particular section, okay. So, this is the straight part, this is what your uc is, right, the core velocity. That is not a function of y, but if you go to a different section, okay, because the boundary layer will be like this will actually, there won't be a sharp kink like that, okay. So, there will be this uc and that uc is different. So, uc is a function of x, but it is not a function of y, okay. So, this is what you get as your uc, okay. And so, this is fairly easy. So, you know that delta by d by 2 is basically 1 minus u by uc. Now, when delta becomes equal to d by 2, okay, equal to d by 2, then 3 into 1 minus u by uc becomes equal to 1, or 1 by u by uc is equal to 1/3, okay, or other words u by uc becomes equal to 2/3. Okay. So, this u then becomes equal to 2/3 of your uc at that particular location obviously. Okay. So, that is what you get. Okay. Similarly, if you take this particular form, okay, and now do the momentum equation. So, one of the key terms that you need to evaluate in the momentum equation is basically uc minus u into dy, right. So, if you do this properly, it will be uc square. Once again, uc is not a function of y anymore. It will be 2 y by delta minus y by delta square 1 minus 2 into y by delta plus y by delta square into dy, right. Okay. So, if you follow through these steps, if you integrate the whole thing out, okay, and you put that back in your momentum equation, the final form that you are going to get is x by d divided by red is equal to 3 by 40 9 uc by u is 2 minus 7 u by uc 16 ln uc by u. Okay, and this is already we showed the steps. Okay, so this is left as a homework. You come from here to here, okay, and this one we have already shown how to do this, right. Okay, so you just use this in the momentum equation. You will get this. Okay, there is a little bit of cumbersome math that is involved. Okay, got it. So, in other words, as we said earlier, so in this case, as you saw, this also uc is actually then 3 by 2 of u. Okay, so it's other way of writing the same thing. Okay, now this particular expression, which is basically the x momentum equation. Okay, now if we at the edge of the boundary layer, where we already saw that uc becomes 3 by 2 of u, right. That means the center line velocity becomes 1.5 times the mean velocity. Okay, if we substitute that over here in this particular expression, right, because they all are uc and u, right, combinations of that. So, then this expression yields x by d becomes equal to 0.026 into Reynolds number d, right. This is almost of the same order as 10 to the power of minus 2 Reynolds number. So, what we got from Blasius was 0.01 Reynolds number d, right. So, this is not way off at all, this is of the same order, this is still 10 to the power of minus 2. So, your x by d at the point of boundary layer merger is basically scales as 10 to the power of minus 2 Reynolds number. Okay. So, this is the thing that you should remember, okay, that this is how we got. So, recapping the whole thing, what did we do? We took the integral equation, okay, and the mass conservation equation. Mass conservation equation yielded this. From here we showed at the edge of the boundary layer your uc becomes exactly 1.5 times of the free stream entry velocity. We substituted that in the momentum formulation and we got that these were the expression, which is basically 10 to the power of minus 2 into Reynolds number, which is exactly the same as what we got in terms of our crude Blasius analysis. This is also crude because this is still integral, but we were able to cast it and show that it is approximately 10 to the power of minus 2. Okay. So, as we said, so there are two things that got established. Your uc actually varies with x, it does not vary with y, and uc is actually a lot higher than the free stream velocity u. This is obvious, this is because your velocity you are losing, there is a velocity deficit due to the boundary layer. So, naturally the mean flow or the uc has to accelerate to make up for that. Okay, so that is pretty obvious that, but this value of 1.5 is something that you should keep in mind. This is of course at the edge of the boundary layer, at the edge of the fully developed regime. That means when after this the fully developed regime completely kicks in. Okay. So, through all this exercise we proved that in the entrance length the boundary layer is still growing, UC is still changing, that means the shear stress will still vary quite a bit. After that, in the developed section we will see, we propose that in the developed section the velocity profile does not change at all, okay, at different sections. We will prove that obviously in the next lecture, we will prove that why that is the case, okay, and we will also show that the next we will also say that what happens now to the heat transfer because of all these flow situations, right. Okay. So, this should be now very clear to you that how we got the developing section and how this developing section can be analyzed, okay, and how the flow velocity will change in the developing section. Of course, we will come to the temperature part when we deal with the developing thermal boundary layer. Okay. Thank you.